In this review, we're going to go over imaginary numbers. Now, if you're anything like me, when I was going through physical chemistry, I hadn't thought about imaginary numbers since seventh grade or sometime in middle school when I first learned about them. But they come back and are useful to us here in physical chemistry. And the reason that they're useful to us is because physical chemistry deals with the wave function. You probably encountered the wave function in general chemistry, and you probably also remember that it has something to do with probability and the determination of different states. And you glossed over this in general chemistry, and we'll go into it in much more gruesome detail in 2 or 3 weeks into the semester. But I want to introduce it here because the probability that you're going to observe any sort of quantum mechanical particle in a certain state is related to the square of the magnitude of the wave function. And we'll get into more detail as to what this means. But the main takeaway here is the wave function itself is not observable, only the probability that you observe quantum mechanical particles in a certain state. And since the probability is the square of the magnitude of the wave function, what that means is that the wave function itself can be negative or even imaginary. And when you square and take the magnitude of a negative or imaginary function, you still can get a positive number in between 0 and 1. You can still get a probability that makes sense. So our wave functions can be negative, they can be imaginary, and they still give real probabilities. And so they can be valid solutions to our wave equation. Again, we'll get into more detail in this as we go into the semester. But I want to introduce imaginary numbers here. So the basic imaginary number you remember is I. And so we just write an I for the imaginary number, where this is a symbol that indicates the square root of -1. So of course, you can't take a square root of a negative number and get a real answer. You get an imaginary answer. And what we'll do with this I is, again, essentially it's a placeholder in these wave functions that we don't have a real way to measure. And so what we'll do, like I said up here, is we'll take the square of the magnitude of the wave functions. So a common symbol for our wave function is this phi, and we can take it and we can take the magnitude of that, which is indicated by these bars around it, and we can square it. And so another way to think about this is what we're doing is taking the complex conjugate of our wave function times our wave function itself. So what's the complex conjugate and exactly why are we doing this? So if we have an imaginary function, so let's say we have a function or a complex function. So our function here is equal to 3i plus 2. If we were to take the complex conjugate of that, what we do is we take every imaginary term and make that negative. So our 3i plus 2 becomes negative 3i plus 2. So the 2, the real term, stays positive. The 3i, the imaginary term, switches from positive to negative. And you can see when we multiply these two together, so if we take the complex conjugate, we're going to get negative 3i plus 2 times 3i plus 2. And what this is going to do, if we just multiply this out like we would in algebra, we get this term here, so negative 9i squared minus 6i plus 6i plus 4. So these two terms are minus 6i and plus 6i cancel. I squared is, of course, -1, so this gives us 9 plus 4 equals 13. So you can see when we take the square of the magnitude here, when we multiply an imaginary function by its complex conjugate, we remove all of the imaginary part. So now we just have 13, which is a real number, and we can scale that down to get a probability. And so that's the main way we're going to be using imaginary numbers. I want to highlight one other aspect that we'll see it in this class, and that is using Euler's formula. So Euler's formula is e to the I theta, where again I is this imaginary number, is equal to cosine theta plus I sine theta. And we'll see this over the course of the semester here. And this is a helpful way to look at wave functions again. So we'll see a couple different kinds of wave function, and they can be, they'll look very similar, but they can be misinterpreted very easily. And so two main types of waves that we'll see are propagating waves and decaying waves. So this here, e to the I theta, is an example of a propagating wave, and that's because the real component of this wave is cosine theta. So if you think of a cosine curve, right? It just goes on like this forever, and it's a propagating wave. So if I was speaking to you and my sound wave was like a cosine curve, it would just keep going on and on and on, and you would be able to hear it wherever you are in front of me. But another type of wave we'll see is e to the something like e to the negative x, right? And you know what this function looks like as well. It's exponential decay. So if I start here and the wave is propagating is going forward is e to the negative x is going to go like this and decay to 0. Um, and these can be very easily, misseen as each other. For example, if you saw something like e to the negative ix, you might think that that is a decaying wave because you have e to the negative x here. But you also have e to the I in there. So if we were to use Euler's formula and plug in negative x for theta, we would get cosine of negative x plus I sine negative x, and which that is equal to cosine of x minus I sine of x. So this is still a propagating wave because we have that I in there. And that's something to keep in the back of your mind as you're looking at different kinds of waves, which again, we'll get into way more in the future. I just want you to be familiar with it here. So the main concepts being Euler's formula and then how to multiply the complex conjugate.